Welcome back to G Fun Facts Online. Today, we are stripping away the science fiction tropes and looking directly at one of the most significant engineering realities of our time. We are talking about fusion energy. For decades, the dream of capturing the power of the stars has been just that, a dream. But something fundamental has shifted in the last 2 years. As humanity stands on the precipice of a clean energy revolution, the Tokamak, a donut-shaped magnetic bottle designed to hold the hottest substance in the universe, has emerged as the clear frontrunner in the race for unlimited, carbon-free power. This is not just a story about heating up gas, this is a saga about defying the limits of nature itself. From the record-breaking sustained plasmas of China's artificial sun, to the raw power outputs of the United Kingdom's jet reactor, and the high-tech wizardry of private companies in the United States, the years 2024 and 2025 have marked a massive turning point in fusion history. We are effectively no longer asking if it can be done. The question has shifted to when it will power our grid. So let's get into the details. To really understand the magnitude of what has been achieved recently, we first have to grasp the sheer audacity of the Tokamak concept. We are trying to build a star on Earth. Now, our sun is a fusion reactor, but it operates on a principle of brute force that is impossible for us to replicate here. That principle is gravity. Deep inside the sun, the crushing weight of 2 × 10 to the power of 30 kilograms of hydrogen creates immense pressure, somewhere around 265 billion bar. Under these crushing conditions, protons are forced together. They overcome their natural electrostatic repulsion and fuse into helium. Here is a detail that surprises most people. This proton-proton chain reaction inside the sun is actually incredibly inefficient by volume. A cubic meter of the sun's core generates about as much heat as a compost heap. The only reason the sun shines so brightly and powers our solar system is because it is absolutely enormous. On Earth, we do not have the luxury of stellar gravity or that kind of size. To make fusion work in a reactor that fits inside a building, we have to compensate for the lack of pressure by drastically turning up the heat. We need to reach temperatures 10 times hotter than the center of the sun. We are talking about 150 million degrees Celsius. At these energies, matter ceases to exist as a solid, a liquid, or a gas. It becomes plasma, a soup of stripped electrons and naked atomic nuclei. Now, this presents an obvious engineering nightmare. No material vessel can hold this star stuff. It would instantly melt any container known to man. The solution is the Tokamak. The word is actually a Russian acronym for toroidal chamber with magnetic coils. Since we cannot use physical walls to hold the core, we use magnetic fields. Imagine a giant donut. Huge superconducting magnets wrap around this donut to create a magnetic field that goes the long way around. This is called the toroidal field, and it acts as the primary cage. But that is not enough. We also use a central solenoid, which is a giant electromagnet sitting in the hole of the donut. This induces a massive electrical current inside the plasma itself. This current generates a secondary magnetic field that twists around the torus in the short direction, known as the poloidal direction. The result of these two fields combining is a helical magnetic field. It spirals like the stripes on a candy cane. This shape is crucial because it traps the charged particles of the plasma in endless loops, keeping them suspended in a vacuum, away from the metal walls. If the plasma touches the wall, the reaction dies and the wall melts, so keeping that suspension is the whole game. Now, let's look at why 2024 and 2025 have been such pivotal years. We have seen a Sputnik moment for fusion, with records falling in rapid succession all over the globe. First, we have to talk about China's marathon runner, the East reactor, often called the artificial sun, located in Hefei. In January 2025, East shattered the world record for plasma duration. They sustained a high confinement steady-state plasma for 1,066 seconds. That is nearly 18 minutes. To give you context, previous records were measured in mere seconds. Why does this matter? Because fusion power plants cannot just run for a few seconds. They need to run 24/7. Achieving high confinement mode, or H mode, which is a state where turbulence is suppressed and plasma pressure jumps dramatically, for over 15 minutes, proves that we can stabilize these volatile reactions over reactor-relevant timescales. East achieved this using fully superconducting magnets and advanced radio frequency heating, proving that continuous operation is engineeringly feasible. While China went for duration, South Korea's KSTAR reactor went for intensity. In early 2024, KSTAR maintained a plasma temperature of 100 million degrees Celsius for 48 seconds. This is the Goldilocks zone for deuterium-tritium fusion. Many reactors can get hot for a split second, but holding 100 million degrees, which is 7 times hotter than the sun, requires mastering the feedback loop of plasma control. A critical part of this success was an upgrade to the machine. KSTAR recently replaced its divertor, which is essentially the exhaust system, with one made of tungsten. Tungsten has the highest melting point of any metal at 3,422 degrees Celsius. This record proved that tungsten components can handle the extreme heat flux without melting and poisoning the plasma. Then we have the grand finale from the United Kingdom. The Joint European Torus, or JET, has been the workhorse of fusion for 40 years. In its final run before decommissioning in 2024, it went out with a bang. JET produced 69 megajoules of fusion energy in a single 5-second pulse. The key here is the fuel. Most reactors run on deuterium because it is non-radioactive and easier to handle. But real commercial reactors will use deuterium and tritium because it fuses much more easily. JET is one of the only machines capable of handling tritium. This record didn't just heat gas, it generated actual nuclear energy, proving that the physics models for the massive international ITER project are correct. Finally, we have the Tungsten Titan, West, in France. In May 2024, West set a record by sustaining a 50 million degree plasma for 6 minutes using a full tungsten wall. The significance here is economic. Older designs used carbon walls, but carbon acts like a sponge, soaking up the tritium fuel. Tritium is incredibly rare and expensive, so losing it to the walls is a deal breaker for commercial plants. Tungsten does not absorb fuel. West's achievement proved we can run long pulses with these non-stick walls, solving a critical economic hurdle. All of the success is built on solving some of the hardest engineering problems in history. Let's look at the magnets. The magnetic cage is the single most expensive component of a tokamak. The older generation, like those used in ITER and KSTAR, use low-temperature superconductors made of niobium tin. These have to be cooled to 4 Kelvin, or minus 269 degrees Celsius, using liquid helium. They are massive, expensive, and fragile. However, we are seeing a revolution with high-temperature superconductors, or HTS. Private companies like Commonwealth Fusion Systems are pioneering magnets made of rare earth barium copper oxide tape. These can operate at warmer temperatures, around 20 Kelvin, but more importantly, they can generate much stronger magnetic fields. We are talking 20 Tesla versus 12 Tesla. The physics win here is massive. The power of a fusion reactor scales with the fourth power of the magnetic field. That means doubling the magnetic field strength makes the reactor 16 times more powerful, or it allows you to build it 16 times smaller. This is why private industry believes they can beat government projects. Better magnets mean smaller, cheaper ships. Then there is the divertor, the ultimate exhaust pipe. As helium ash builds up from the fusion reaction, it has to be removed, or it chokes the fire. The divertor sits at the bottom of the tokamak and faces the greatest heat flux of any object ever built by man, equivalent to 10 to 20 megawatts per square meter. That is like pressing your hand against the surface of a re-entering space shuttle. Innovations here are moving away from solid blocks to monoblocks, small tiles of tungsten bonded to copper cooling pipes, which KSTAR and West have proven can survive the hellish conditions. We also have to talk about taming the beast, specifically plasma instabilities. Plasma is essentially an electrical fluid, and it hates to be caged. It thrashes around, creating instabilities like edge-localized modes, or ELMs. Think of these like solar flares on the surface of the plasma. If they touch the wall, they can melt the tungsten. There are also disruptions, where the entire plasma current collapses in milliseconds, slamming millions of amps of current into the reactor walls. The fix for this is incredibly high-tech. Modern tokamaks use resonant magnetic perturbations. These are small, precise magnetic coils that tickle the edge of the plasma to release pressure gently, acting like a safety valve to prevent the big explosions. While the massive international project ITER in France slowly marches toward its first full-power operations in the mid-2030s, the commercial race is heating up with agile startups trying to leapfrog the timeline. Commonwealth Fusion Systems, spun out of MIT, is currently building Spark in Massachusetts. It is designed to be the first machine to achieve net energy, meaning it produces more fusion heat than the electricity used to heat it. They have already successfully tested their HTS magnets and aim for first plasma by late 2026 or 2027. If they succeed, it validates the high-field compact reactor approach. Across the pond, Tokamak Energy in the UK is using a different shape entirely, the spherical tokamak. Instead of a donut, it looks like a cored apple. This shape is naturally more stable and efficient, requiring less magnetic power to hold the plasma. Their ST40 reactor was the first privately funded machine to hit 100 million degrees Celsius, and they are now designing a pilot plant to demonstrate grid-capable power. But perhaps the best news for fusion recently came not from a physics lab, but from a regulator's office. In 2023, the U.S. Nuclear Regulatory Commission voted to regulate fusion plants as particle accelerators rather than nuclear fission reactors. This is huge. Fission regulations require billions of dollars in capitalization, massive exclusion zones, and decades of licensing due to meltdown risks and high-level waste. Fusion has neither. There is no risk of meltdown because if a fusion reactor fails, the plasma cools instantly and the reaction stops. It is like blowing out a candle. Physics makes a runaway reaction impossible. There is also no long-lived waste. The primary byproduct is harmless helium. The steel walls do get radioactive, but the half-life is short, about 100 years, compared to 10,000 plus years for fission waste. This decision drastically lowers the barrier to entry, allowing startups to build pilot plants near cities and industrial centers. Current projections suggest fusion could achieve a levelized cost of electricity of $60 to $70 per megawatt hour. While that is higher than wind or solar, fusion provides baseload power. It works at night and when the wind isn't blowing. It is the perfect clean partner to renewables, potentially replacing coal and gas plants entirely without needing massive battery storage. To conclude, the artificial suns of Earth are rising. The records set by East, KSTAR, and JET in 2024 and 2025 are not just data points. They are the proof of concept for a new era of civilization. We have mastered the magnets, we have tamed the heat, and we have begun to forge the materials that can withstand the heart of a star. For decades, the joke was that fusion is 30 years away, and always will be. That joke is now obsolete. With the physics proven and the commercial race igniting, fusion is no longer a question of physics, it is a question of engineering and scale. The star power age is dawning. Thanks for listening to G Fun Facts Online.